Hey everyone, I'm Darwin Mbora, an aircraft mechanics student at Philippine State College of Aeronautics, and today I'll be presenting our research to you guys. I apologize for not using the prescribed background because my device cannot support virtual background options as of now. So our research is entitled Sheet Metal Corrosion Rate, Use of Non-Aviation Anti-Corrosion Products. This is an experimental research where we utilize scientific approach. Here, we manipulate variables to show different outcomes and make use of the experiment that is being performed to collect the data at different time points. In this way, we will be able to determine the cause-effect relationship of each variables and the data that are gathered. So in aviation, we all know that corrosion is an inevitable part of aircraft corrosion treatment. While aerospace industry is continuously developing new and better materials, progress is offset partly by a more aggressive operational environment of the aircrafts and by the complexity of the corrosion phenomenon. The resistance of aircraft materials to corrosion can drastically change by just a small amount of environmental change. As researchers, we wanted to introduce non-aviation corrosion prevention products that are being used casually in our day-to-day treatment in our households. The idea is that these non-aviation anti-corrosion products could potentially offer the same level of effectiveness like the acid-based allodyne, which is commonly used on small aircraft corrosion treatments. The first product is the mineral oil, which is a common lubricant that is often used to apply in tools for corrosion and rust protection. The second and the third one are the WD-40 and the shear car. They are well-known specialist corrosion inhibitor, and they are multi-purpose product used to apply in any surface where corrosion can possibly reside. The researchers who envision themselves to become aircraft mechanics in the near future are also concerned in the field of science and engineering, specifically in aircraft maintenance corrosion treatment. We have taken interest in experimenting these three introduced anti-corrosion products, WD-40, shear car, and mineral oil. It is on this premise that we initiated this investigation for the purpose of knowing the possible anti-corrosive effects of these products to the corrosion rate of aircraft sheet metal. The major contributors of the corrosion deterioration of sheet metals are hostile environments factors and climate conditions. This is a common continued challenge for approved maintenance organizations, specifically at Genab Mactan in Lapu-Lapu City, Cebu, an island city in the Philippines where the air is mostly moist and hot. This study measures the corrosion rate of aircraft sheet metal coated with non-aviation anti-corrosion products, WD-40, shear car, and mineral oil. The corrosion rates were calculated using the corrosion rate formula R corrosion 87.6 constant times W is weight loss over D for density, A for area, and T for time. And the p-value were determined using SPSS statistical tool software and by using a 0.05 level of significance to look for the significant difference between the result between the data. Statement of the problem. The main focus of this study is to experiment the effects of the introduced different anti-corrosive products to the corrosion rate of aircraft sheet metal. Specifically, this study seeks to answer the following subsidiary problems. So in order for us to get the cause-effect relationship, we need to identify first the corrosion rate of aircraft sheet metal without anti-corrosive product and corrosion rate of aircraft sheet metal with anti-corrosive products, which is the before treatment and the after treatment. So subsidiary problem number one is what is the status of corrosion rate before the treatment at 336 hours and 672 hours. Subsidiary problem number two is what are the different anti-corrosive products that will be used in the after treatment. And subsidiary problem number three is what is the status of the corrosion rate of aircraft sheet metal after the treatment on experimental group at 336 hours and 672 hours. So after knowing the status of corrosion rate on before treatment, which is no coating, and after treatment, which has three coatings, WD-40, shear car, and mineral oil, we now then need to know if there's a significant difference between them. So number four will question if there's a significant difference in the status of corrosion rate of aircraft sheet metal between before treatment and after treatment. And the fifth and final subsidiary problem is which of the three introduced anti-corrosive products is the most effective in mitigating the corrosion rate of aircraft sheet metal. Theoretical framework. Here you can see the whole procedures of our experiment. We have before treatment and after treatment. Before treatment means that the aircraft sheet metal was not coated in any anti-corrosive products. And the after treatment means that the aircraft sheet metals were coated with three anti-corrosive products: WD-40, Shirka, and mineral oil. All in all, there are four aircraft sheet metals that is being used, one in before treatment and three in the after treatment. The pre-test post-test are the two time points of the study. Here we have collected the data needed to compute the corrosion rates of aircraft sheet metal. Research methodology. Here we have data gathering procedure for the before treatment and after treatment. Both treatment will undergo the same procedure, but the only difference is that the before treatment will not have any anti-corrosive product on its aircraft sheet metal. So the first piece of aircraft sheet metal was immersed with no coating at a plastic cup with a vinegar, hydrogen peroxide, and table salt mixture up until to the end of experiment, or at the second time point 672R. Same goes to the after treatment. The second piece of aircraft sheet metal was coated with WD-40. The third piece was coated with shear car. And lastly, the fourth piece was coated with mineral oil. So the data that we will be gathering are the weights of aircraft sheet metal from before, during, and after the experiment. A digital weighing scale was used to identify the initial and the final weight of each aircraft sheet metals. The corrosion rates of aircraft sheet metal before and after treatment were then computed using the formula R corrosion 87.6, which is constant, W for weight loss over D for density, A for area, and T for time. At the middle of experiment timeline, which is 336R, the corrosion rate of sheet metal from before and after treatment were also computed. And lastly, the final data was taken at the end of experiment timeline, which is at 672R, and their corrosion rates were also computed. So the Wilcoxon non-parametric test was used to determine the significant difference in the corrosion rate of aircraft sheet metal between before versus after the treatment in 336Rs and 672R. SPSS version 21 was used to perform the non-parametric test, and to test the hypothesis, and the critical value was set into 0.05 to determine the level of significance between the corrosion rates. So let's proceed to the results and discussion. If you guys remembered, statement of the problem 1 will identify the status of corrosion rate on before the treatment. So at before treatment, it has a corrosion rate of 126.28% at 336 hours and 94.71% at 672 hours. Both are significantly higher, but this is expected since there's no anti-corrosive products being used on this treatment. Statement of the problem 2 will identify the anti-corrosive products being used on the after treatment, and they are the WD-40, shear car, and mineral oil. Statement of the problem 3 will identify the status of corrosion rate on the after treatment experimental group. At the WD-40, it has a corrosion rate of 35.89% at 336R and 42.99% at 672 hours. Both are significantly lower compared to the before treatment corrosion rates. Shear car at 336 and 672 are a little bit higher compared to the WD-40, and the mineral oil at 336 and 672 has the highest corrosion rate of them all, which is closer to the before treatment corrosion rates. So the lesser the corrosion rates, the more effective the product is. But the higher the corrosion rates, the less effective the product is. Statement of the problem 4 will determine if there's a significant difference between before and after treatment using the SPSS 21 statistical tool software. Before treatment versus after treatment, WD-40 has an interpretation of significant on both 336 and 672 hours. This is because their p-value is lower than the crit value 0.05. Before treatment versus after treatment, shear car still has an interpretation of significant at 336 and 672 hours. This is because their p-value is still lower than the crit value 0.05. But it is important to take note that the p-value of shear car at 672R is marginally close to the crit value 0.05. And lastly, before treatment versus after treatment mineral oil has an interpretation of significant at 36 hours, but not significant anymore at 672 hour. This is because the p-value of mineral oil at 672 hour is higher than the crit value now. Statement of the problem 5 asks, which of the three introduced anti-corrosive products is the most effective in mitigating the corrosion rate of aircraft sheet metal? So based on the findings of our study, we have found out that all three introduced anti-corrosive products are effective, at least at the early parts of the experiment. Their level of effectiveness changes, it decreases as the experiment continues, resulting to mineral oil rendering not effective anymore at the end of experiment. With WD-40 yielding the most significant results from both start and later parts of the experiment, followed by shear car and then mineral oil, we can conclude that WD-40 is the most effective anti-corrosive product in mitigating the corrosion rate of aluminum cadmium 2034 T3 or aircraft sheet metal. And that's it for our study, guys. Thank you so much for listening. Have a nice day.